We're ready whenever.
Yeah. Right, hello, welcome for our Monday colloquium. Thanks all for coming. I'm very excited to introduce Professor Andrew Stewart from UCLA, who will be talking to us about polar oceanography, which you might understand I'm quite excited about. So is Hannah. Andrew is originally from Scotland, did his master's in mathematics, and you did the bachelor and master's together, right? So the British system allows you to sort of bunch them into 1 degree in mathematics from the University of St Andrews, and then a PhD in math at Oxford. We had a brief encounter. There's a math competition called the Woolly Owl, for which as I was at Cambridge, we traveled to Oxford, and
who won? I was going to say.
And I was debating on whether to bring this up or not. Oxford was declared the winner in that year by some measure of subjective assessment. We haven't talked since, but now it's been what, 13 years, so I feel like we've come back together. Andrew then went to stayed at Oxford for a bit, went to Caltech to do a postdoc there, and has then been a professor in atmosphere and ocean sciences at UCLA ever since. Please join me in welcoming our speaker, Andrew Stewart.
Thank you very much, everyone. Thank you, Till, for the kind and honest introduction. And many thanks for inviting me here today. This is my first visit to Madison, indeed to Wisconsin, and certainly to this department, and it's been a real pleasure meeting many of you over the course of the day and getting to see your lovely campus and city. As advertised, my name is Andrew Stewart, and I'm a professor at UCLA. I've entitled this work, Melt-Driven Transport of Oceanic Heat Toward the Antarctic Ice Sheet. And I'm sort of hoping that that sounds a little backwards to the story you might expect to hear. In case you had no preconceived notions whatsoever about how this should work, you might expect that movement of warm water up toward ice in the ocean would lead to melt. Whereas this title seems to imply the opposite causality. In some sense, the melt is somehow sucking in ocean heat toward the ice. And so later in this talk, we'll see how that could possibly happen. Inspired by this finding, I'll move on to talk about a new theory, or perhaps even parameterization, of Antarctic ice shelf melt that we're working toward implementing in Earth system models. The real stars of the show here are, of course, my current and former graduate students, Yidong Fong So, MIT, and Garrett Finucane, who's still at UCLA. Briefly, because I have never been here before, I thought I would briefly just introduce myself scientifically. If you want to categorize me as a scientist, I would say I'm a physical oceanographer with primary interest in ice-ocean interactions, the deep ocean circulation, and mesoscale eddy dynamics, among various other things. To give you a sense of the kinds of things that go on in my research group, there's really hardcore GFD, in this case looking at the interaction of ocean mesoscale, the eddies with oceanic western boundaries. We use regional models. For example, this regional model of the Weddell Sea showing around near Antarctica, showing temperature field at mid-depth, hinting at temperature sneaking its way toward the ice, is a tool we use to better understand near Antarctic circulation. We use, but do not make, observations. For example, we have a couple of projects going on right now using measurements made by seals that some very industrious people have attached instruments to, and using their measurements to help us better understand the eddy field beneath Antarctic sea ice. And we can even turn to the dark side of machine learning, in this case trying to see how we can use satellite measurements to make inferences about changes and variability in the global overturning circulation, not just in the Southern Ocean, but actually in all the ocean basins, with a view to providing an indirect monitoring system. And of course, all of this is largely led, not by me, but by this group of people here, some of whom have now left the group, but this is a recent photograph. And of course, the most satisfying part of my job is getting to interact with these folks. I hope anyone watching from home caught that particular compliment. So the work I'm talking about today is most closely related to number 2 up here, related to the way the ocean interacts with the Antarctic ice sheet, about this question of heat in the ocean, its role in melting Antarctic glaciers, and the consequent retreat of those glaciers. So, the high-level motivation for understanding the ocean's interaction with glaciers is sea level rise. This is a plot that many of you will have seen. This is the projected future sea level rise, total sea level rise from the latest IPCC report. As you can see, there's substantial uncertainty, a wide range of future projections. That uncertainty is particularly pronounced for the Antarctic contribution to future sea level. Unfortunately, the axis here is negative, so yeah, it increases down. The range projected based on dynamical and statistical models is somewhere in the order of 8 centimeters plus or minus a lot, even verging into negative numbers, suggesting that within the envelope of our confidence, you could even have a decrease in sea level due to Antarctica. And the fundamental reason for this uncertainty is shortcomings in our understanding of ice ocean processes and their representation in future projections. Just to orient you with respect to the environment we're talking about here, this is a cartoon of the Antarctic ice sheet. The ice is white, overlying bedrock, and the ocean is over here in blue. These parts of the ocean here that float on top of the ocean are called ice shelves. They're supplied by accumulation of mass in the middle of the continent that flows out toward the edges and ultimately, in various places around Antarctica, float over the ocean. To give you a sense of scale, these are hundreds of meters of ice overlying hundreds of meters of ocean and spanning areas that are up to hundreds of kilometers in width. So they're very large chunks, volumes of ocean. Now these images come from a not particularly scientific source, so don't scrutinize them too closely, but they do look cool and convey the gist of the key points I'm trying to convey here. Now the uncertainty in our projections is again due to limitations in our ability to project future evolution of the ice sheet and its interaction with the ocean. In what is rather arbitrarily referred to as West Antarctica, and there is no West, I don't make the rules, in this part of Antarctica over here, much of the ice sheet is actually below sea level. And this makes it particularly susceptible to potential future retreat. And the pacing of that retreat is particularly uncertain, with some future projections suggesting that it could retreat enough to produce a meter of Antarctic contributed sea level by the end of this century. In fact, I think the more recent runs with this same model revise that projection down to more like half a meter. These particular runs account for specific kinds of dynamical instabilities in the ice itself, which are triggered by oceanic melt, and make it particularly susceptible to retreat. These projections are so far above the other projections I showed you earlier, they're actually given as a separate category in the IPCC report. But all of this is to say, the takeaway is that we're really motivated to better understand the processes governing the ocean's interactions with the ice, because there remains so much uncertainty regarding the future evolution of the Antarctic ice sheet. So, how does it come to be that the ocean triggers retreat of Antarctic glaciers, be it slow or rapid? Well, oceanic melting of the ice is an important component of Antarctica's mass balance in general. The accumulation of mass in the interior is balanced by ice falling off the ends of the ice shelves, calving, and by melting of the ice from below in comparable portions. The most rapid ice melt occurs when relatively warm waters, which actually sit in the subsurface ocean, and warm here means about 2 degrees Celsius, accesses these ice shelf cavities, as they're called, parts of the ocean that sit beneath the ice shelves, and then melts the ice from below. This is more conceptually illustrated in this diagram on the right, which I have Yong Su to thank, in which the warm water conceptually is the kitten or kitten's tongue. The ice sheet is the ice cream, and the licking of the ice by the tongue causes it to retreat. Incidentally, I have done more research into this image, and I can tell you that feeding ice cream to cats is not recommended by veterinarians. So, you're not trying this at home. Yeah, don't say you didn't learn anything useful in today's seminar. Okay, so how does this tongue of warm water get to lick the base of the ice? Well, if we look at this particular region of the ice, this is a map of all of Antarctica's ice shelves, which are the coloured regions around the outside, showing the rate of actually ice thickness change, which is slightly different from melt, in meters per year from Reno et al. 2013. This particular area, the Amundsen Sea embayment, is heavily studied because it has the highest rates of melt and has been suggested to be particularly susceptible to rapid retreat of those ice sheets because of their sitting below sea level. Fortunately for the warm water, there exist troughs carved into the continental shelf all around Antarctica by glacial cycles, glaciers advancing and retreating. For example, in this area here, the Amundsen Sea, the colours here show bathymetric depth. The green is deep and red is shallow, and there is a trough leading from the shelf break here, here's the open ocean, all the way back to the ice shelves in grey here. Along these black dots, temperatures measure temperature and salinity from ships in the ocean and from robotic submarines inside the ice shelf cavity over here, show that warm water, the kitten's tongue, reaching all the way into the ice shelf, actually getting all the way up to what's called the grounding line, where ice meets ocean meets land. So we can really see, and these measurements are extremely expensive and difficult to make, by the way, we can really actually see that warm water accessing the ice shelf base all the way from the continental shelf break. And we can see it doing it through these troughs in the continental shelf. But how is it that warm water comes to be steered into these troughs? Now we're looking at the same area, and the blue shows bathymetric depth. Grey, again, is the ice shelves. Excuse me. Colours are bottom temperature of the ocean water from a regional model, and black arrows from the same model are mean current speed at the seafloor. And what this figure shows us is that there are a series of what are called undercurrents flowing eastward deep along the continental shelf break that are the supply of this warm water into the troughs and up to the ice shelves. If we took a transect across somewhere like this is actually not where the transect's from, but it's not that different. And these are actual observations showing the velocity in and out of the page. Then we see that there is a eastward flow out of the page near the seafloor at the shelf break in that warm water layer, and a westward flow into the page of the colder surface waters. We can actually identify in this plot on the right, in this case, 3 different troughs just in the Amundsen Sea, but these really are everywhere around Antarctica, where these undercurrents cross the trough at the mouth and then flow down the eastern side, carrying that warm water to the ice shelves. So we've been able to, through a series of modelling and observational studies, to really pick out these pathways by which this warm water is getting from the open ocean where it's abundant and wending its way into the ice shelf cavities. Oops. And this has motivated various studies to really try and better understand what controls these undercurrents and the amount of water that they move in onto the continental shelf and into the ice shelf cavities. This is a study I co-authored a few years ago with collaborators from the UK, in which we showed that there is a strong correlation of interannual timescales between the ice shelf basal melt in blue, they're all normalized here by the way, the speed of the undercurrent in red, and and it's anti-correlated with the winds, which are basically the black curves. So weak winds, the winds on average blow westward along the shelf break. When they're weak, there's stronger undercurrents and more flow into the continental shelf, more heat transport and more melting of the ice shelves. And this has actually been taken much further beyond Antarctica. For example, links have been drawn between the variability in the winds along the Antarctic continental shelf break and the Amundsen Sea embayment, which is down here, and actually tropical Pacific variability via teleconnections in the atmosphere, radiation of Rossby waves that particularly excite this structure, the Amundsen Sea low, which is the source of these westward winds along the Antarctic continental shelf break in this region. And these teleconnections have been suggested to be responsible for accelerations and decelerations in the rates at which these Antarctic ice sheets are melting. So the colored curves here are melt rates of different ice shelves. The black is basically an indication of the strength of those winds, and essentially the argument the authors made, which I'm going to acknowledge is not super clear, is that when in times when those winds are strong, the melt, which has been increasing over time, has kind of stopped increasing as much for a while. And then when the winds have weakened off, the melting has gone up a lot more. So the story that has been coming together collectively has been that there is, among other various kinds of climate variability, including tropical Pacific variability, resulting in fluctuations in the winds over the Amundsen Sea embayment, resulting in acceleration and deceleration of these undercurrents that transfer warm water toward the ice shelves, which then increases and decreases the rate at which these ice shelves are melting. The evidence is still kind of being assembled, but there's a growing body of evidence that supports these connections.
Can I ask, is it known whether there's a relationship, if the wind is driving this, does it also drive an expansion or contraction of the ice, sea ice? Is that related?
Yes.
Okay.
Yes. It's a kind of quite separate question about what controls Antarctic sea ice variability and the long-term trend in Antarctic sea ice. Especially recently, there's been a lot of attention paid to this matter because for decades there was essentially no trend in Antarctic sea ice extent, and then all of a sudden, for a few years, there seems to be a sudden state change where we've jumped to less sea ice, statistically well below the envelope of what we had before. And what's dry is this is a very active current of political research, and the winds are playing an important role in moving. These coastal regions are kind of sea ice factories because the winds blow the sea ice away from the edge, open up water, and new sea ice is formed. This is all relevant, but not directly tied to the story I'm going to be telling today. Yeah. Now the gap, or the hole in the logic in this story, is that this mechanism via which atmospheric variability influences these undercurrents doesn't really have any clear mechanism. Right? We don't actually really, or didn't, understand why these undercurrents should exist at all. To make that argument clearer, if we actually look at what we might think of as the external forcings of circulation around Antarctica, this is the zonal winds, moderate-scale average zonal winds around Antarctica, and this is tidal flow speed, mean tidal flow speed around Antarctica. It turns out both of these favor driving flow to the west. The winds push the water to the west at the surface. Sloshing of tides back and forth across the continental slope actually creates rectified mean currents that are also west, particularly at the seafloor, particularly over the continental slope. And so, excuse me, it's not obvious at all why we should have undercurrents, or why these why fluctuations in the winds, for example, should be causing these undercurrents to fluctuate and the amount and the melt rates of these ice shelves to vary. And so, our question is what we started with, was why is it we have these undercurrents in the first place? We went thinking, this project, thinking that the key to constraining future changes in Antarctic ice shelf melt in some places like the Amundsen Sea and Bayman is to understand what sets the heat transport carried by these undercurrents. I ultimately to understand what environmental factors control the melt rates of Antarctic ice shelves. This is the big question, right? If we know that if we can understand this, then we'd be a long way down the road to better constraining the future of the Antarctic ice sheet. But the problem is that this question remains unanswered. And unfortunately, I've somewhat spoiled the answer for you in the title of my talk. But if you could all play along and act surprised at appropriate points, then it would look really good on the recording of this talk. Did I mention I'm from LA? And we'd like to, and the reason we'd like to answer these questions is for their obvious relevance to the way Antarctic ice shelf melt rates will respond to climate perturbations. Now there are different ways one could answer a question like this. Various previous studies have looked at the behavior of undercurrents using regional models, for example, and have tended to struggle to obtain dynamical insight because of the complexity of those models. So we tried to take a different approach, which was to try and assemble the minimal number of ingredients that one would need in order to produce an undercurrent in a simulation of this region. And this is what we, or really I should say, UW, came up with. Here is a very idealized representation of the Antarctic continental shelf, slope, ocean, an ice shelf, as simple as could possibly be, with a trough. All the ingredients we just said were important in this first part of the talk. And essentially just prescribed stratification around the boundaries. There's also a couple of other details. There is sea ice in the model, there's a prescribed steady wind, and it's really minimally complex. Very, very importantly, we do not, in any of the boundary conditions, impose that there should be any kind of undercurrent. So the east and western boundaries have zero flow in the subsurface and only westward flow in the surface. No eastward flow anywhere. So if any undercurrents emerge in these simulations, then it's purely an intrinsically forced behavior. It's not imposed by the boundary conditions. So I'm going to show you that this model, as simple as it is, actually not the simplest thing we tried, but this model, as simple as it might be, produces a not bad representation of the circulation as compared with what we see in the real Amundsen Sea. As suggested by this 3D rendering earlier, there is in fact an undercurrent in this model. And what I've done to show you this is I've taken a couple of slices. This is looking down on the wall domain, showing the bathymetry in these dotted lines. Ice shelf is here, south of the grey line. And I've taken a couple of slices, one here and one in the middle of the trough. And these red patches here correspond to eastward flow out of the page. Blue is westward flow into the page. I put the observations down there again so you can see it produces undercurrents with a very similar strength and structure to what we see in observations. The panel on the left also shows in the green arrows the depth integrated transport in the warm water layer where the temperature is greater than 0 degrees Celsius arbitrarily. And also in the colors, the heat transport toward the ice in that warm water layer. So red is heat transport south, blue is heat transport north. And what we see is there is the formation of undercurrents with a cyclonic circulation, negative vorticity in this trough that delivers heat to the ice and induces melt. Now the nice thing about a model like this is that you can relatively cheaply perturb it to understand how it works. I'm actually not going to talk about these experiments at length because I have, I think, more insightful experiments to show you, but in short, we conducted a variety of experiments with this model with varied winds, tides, vertical diffusion, changes in the geometry, bedrock elevation, and the width of the trough. We even ran simulations with no trough, in which the behavior is actually kind of weird, but that's really qualitatively different from what we find around Antarctica. I don't have time to discuss all these results, but essentially we produce the result we expect, that there's a strong relationship between the strength of the undercurrent on this axis and the melt rate of the ice shelf, except if we actually remove the trough altogether. And so this is again consistent with previous thinking, that the undercurrent is what delivers heat to these ice shelves. However, there are some surprises here. For example, varying the wind, these two triangles here, produces almost no change in the undercurrent. This is completely contrary to previous studies, and I can come back and discuss why I think that is later. But the gist of it is that these experiments didn't in any way suggest somehow that the external forcing of the system was what was driving changes in the undercurrent strength and in the melt, with the exception perhaps of the tides, but that's really a more complicated story. And so we have the alternative hypothesis, as again as suggested by the title of the talk, that the undercurrent is in fact really a buoyancy force flow, and that the buoyancy forcing that is relevant for driving that flow is in fact the melt of the ice shelf itself. So how can we use this idealization to test this hypothesis? The way that we proceeded here was that we took this model, which again I'm showing conceptually in this diagram here, and we ran a series of experiments where we prescribed the freshwater, meltwater input at the base of the ice. So which we ramped up from 0, actually, so basically the ice shelf is now a concrete block, and we just impose a certain amount of fresh water into the ocean. So the ice shelf and its melt cannot respond to the ocean whatsoever. And the question is, does that produce an undercurrent and produce intrusions of warm water toward the ice? And I should note that this is not the only possible situation that could occur if you dump a bunch of fresh water into the ocean. It's quite plausible that you could draw in lighter water into the cavity and transform it into even lighter water, for example. Or you could draw warm water into the cavity, not from the shelf break, but from east or west of the cavity. It's far from a guaranteed result. So we're going to vary the amount of fresh water we dump into the ocean and the ice shelf. We're essentially posing the ocean through the base of this ice shelf and see what happens. So I'm showing you now these four experiments where we go from 0 meltwater input up to 24 meters per year equivalent, which is a very rapid melt compared to most ice shelves, over the entire ice shelf. As we do that, we see increasingly strong undercurrent flow into the trough and transport of warm water into the ice shelf cavity. Again, that didn't have to happen. This increase in water could have drawn warm water into the cavity from over here. It could have transferred lighter waters into even lighter waters. It didn't have to create an undercurrent. We didn't cook this. But it does. Consistently draw waters from the shelf break, driving an undercurrent and pulling it into the ice shelf cavity. These panels on the right show the cumulatively integrated heat transport across the ice front from right to left, and show that the heat transport into the cavity always happens right in the center, in the trough. So it really is the heat brought out by the undercurrent that is entering the cavity and driving balancing the meltwater in. Yeah.
So a quick question. The melt that you prescribe it along the line or along the wall base or?
It's uniform over the entire ice base. So why does that happen? It seems backwards. Why does melt drive the undercurrent and not vice versa? It's clear, it's an experimental result, but it's conceptually confusing. So I think one way to understand this, the simplest way to understand this, is that, as indicated in this diagram, any warm water that's in contact with the ice pretty much immediately causes melt and gets transformed into fresh meltwater. And so the ice basically immediately consumes any warm water that's in contact with it by melting, and gets rid of it, transferring it into lighter water. So in some sense, you can think of this as like an upside down bathtub. Like this, if you turn on the melt, it's like you're opening the drain, and that warm water or your bath water just starts pouring away down the drain or pouring up away down the drain. And just like in the bathtub, you create a pressure gradient that drives flow on toward into the cavity, drives more light. So it's sort of, in that, if you think of it that way, it's kind of obvious that if you're draining the water away, then more must come in to replace it by creating a horizontal pressure gradient. But it's a little bit more subtle than that, because as we've seen before, it's not just a straightforward pressure-driven flow. It's actually a rotationally dominated, largely geostrophic flow, and it actually forms a cyclonic circulation, drawing that warm water in from the shelf break into the trough and into the ice shelf cavity. And the short version for why this happens is that it's vortex stretching. This upwelling, I mean, if I was teaching my undergraduate physical oceanography at a class, as I will in a few weeks' time, I would be doing ballerina twirls to demonstrate the same principle. But you don't need to see that because you all know it. That the upwelling of this water, transformed from dense, warm, circumpolar deep water to lighter, fresh water, is actually serves as a vorticity forcing on the circumpolar deep water layer. And in fact, it's this upwelling, the convergence of water in the circumpolar deep water layer via the action of the Coriolis force serves to accelerate that water cyclonically, i.e. to drive a clockwise or cyclonic circulation in the circumpolar deep water layer that draws that water in from the shelf break. Now, I'm kind of hoping that you're going to accept that story at face value and not make me go through the following 10 slides of vorticity budget analysis that I have, that I was rather hoping to skip in the interest of time. If you do like to see the gory details, I am ready to roll. I'm hoping that you'll just, but maybe at the end of the talk I can come back to it. The gist of it is if you dig into the vorticity budget, you really can show, after great effort, that the vorticity budget of the warm water layer, specifically, this upwelling is an input of cyclonic vorticity. It's locally balanced by, essentially by flow across the mean potential vorticity gradient. That is necessarily balanced elsewhere by topographic steering, a bottom pressure torque that steers warm water into the trough at the shelf break and drives it toward the ice. So you really can explicitly make this link between the vorticity input in the cavity from upwelling and melt to steering of the fluid into the trough at the shelf break. It does exist, I promise you, and I can show you the slides if you're interested. But it really is a lot of analysis, and that ultimately is the reason. So, yeah.
I'm inclined to believe this conjecture because I was thinking naively that the melting ice would cool the water more than freshen it, and so it would sink, and therefore with the intake you'd get an easterly current at the top, and the outflow you'd get a westerly current from just conserving angular momentum. But you say that it's upwelling, and that
it's upwelling. The freshening
winds by far. So
by far. Yeah.
Totally wrong.
Oh, close. Yeah. And actually, that sense of circulation you described, I will come back to in a second. Very relevant to the next part of the talk. The gist of all of this is that we're arguing here that this causality, far field or climate variability, to driving undercurrent variations, to driving melt, doesn't hold up. That really this is not the right linkage. In fact, this is driven by this. And kind of calls into question the current way we're putting together this chain of events that are driving variations in Antarctic melt. Now, you might be thinking, well, that's kind of a negative story. Basically, you just said community thinking is wrong, and that's too bad. And so rather than leave you on that, I'm going to try and end on a more positive note by talking briefly about this, how we might more accurately go about understanding the melt of Antarctic ice shelves and its relation to changes in the ocean state. And this, which involves also turning from a question of conceptual understanding to also one of practicality. How might we parameterize or represent this process of Antarctic ice shelf melt in Earth system models? This is a map we've already seen, showing the thinning rates of Antarctic ice shelves. And as we noted earlier, the rates at which these ice shelves are melting or losing mass or changing around Antarctica varies substantially. It's kind of hinted at in this diagram, which also shows the temperature of the water on the continental shelf above freezing, that a key link in understanding this is the temperature of the waters on the continental shelf, and I'm not disputing that at all. But the state of the art in making projections, dynamically based projections about these ice shelf melt rates is still evolving. where there has been substantial effort in the past decade, especially to develop coupling between ice sheet models and Earth system models. For example, as is still going on in the ice sheet model into comparison 6, and to help us improve these future projections. But to be frank, it is going to be a challenge for decades to come, because we are not close to representing the flows in ice shelf cavities in Earth system models. This is a really extreme example showing a 3-degree, not cost-scaled, flat-long grid for a particular Earth system model that was used as a test of an ice shelf model parameterization. But the standard 1-degree IPCC class models are not much better, and they're far from resolving the first order rates of deformation rate, which is something like 2 to 5 kilometers in these ice shelf cavities. So to resolve the boundary currents and circulation features that you need to get the melt rates right, we're really far from that, and are going to be for the foreseeable future. So, in the short term, realistically, I would argue, parameterizing the ice shelf melt rates in Earth system models is the way forward. There exist ice shelf melt parameterizations. For example, a very nice recent paper evaluated a bunch of these recent parameterizations using a high-resolution regional model, and the summary of is that basically all these parameterizations in some form take information that's given about the structure of the ocean, temperature and salinity in the far field, and in some way or another map it to the base of the ice in order to locally estimate how much melt should be going on. And unfortunately, they seem to fare rather poorly at doing this. So here is the root mean square error using far field temperature and salinity to predict melt across all different ice shelves for various different existing parameterizations. And just for context, 60 gigatons per year would be more than the mean melt rate for all but 8 of the 70 or so Antarctic ice shelves. So that's a big error. So this is a part of the motivation for the work I'm about to show you. The other part is a more fundamental interest in better understanding this control and circulation of ice shelf cavities and its relation to melt. Now this work is partly inspired by the work I just showed you, which showed that there is an important link between the melting of ice shelves and the vorticity associated with that melt and the circulation adjacent to the ice shelves that influences the melt. Now if you drank the Kool-Aid during that particular part of the talk, then you may be thinking, well, obviously the way to go here is to use the vorticity budget to predict the heat transport into the ice shelf cavity. And I'd say, great idea. I love that idea. But unfortunately, generalizing the circulation generated by melt input vorticity forcing in very complex Antarctic continental shelf geometries turns out to be very difficult. And so we took a different tack. The theory I'm going to present to you has 2 elements. The first is dealing with the complexity of the geometry of Antarctic ice shelf cavities, and it's inspired by the well-established finding that, and this is probably not going to come as a huge surprise, in order for warm water to possibly access ice shelves, the warm water has to be at least as high, or at least higher than, whatever bathymetry serves as an obstacle between it and the ice shelves, in this case, the continental shelf break. Conceptually, if this is our idealized ice shelf, and this is your warm water, the warm water must rise at least higher than whatever this depth is in order to access the ice shelf cavity. And this depth we call the hub, or highest unconnected isobath. That's whatever you can call it, whatever you like. And so, without diving into details, part of what Garrett did was to go around all of Antarctica's ice shelves and construct algorithms that identify this hub, this bathymetric obstacle to warm water inflow everywhere, even in these generalized, very complex geometries. This is an example of expulsion of one ice shelf cavity, one of the biggest in Antarctica, showing 2 isobaths. The red one and the green one is 660 meters, the red one is 650 meters. And you can see that at 660 meters, the isobath, this green isobath forms a kind of closed bowl enclosing the ice shelf cavity, which is kind of down here. But at 650 meters, the red isobath, it's actually connected to the open ocean. So for that particular ice shelf, the hub is 650 meters. So that's how high the hot warm water has to be at least to possibly melt the ice shelves. Yeah.
What's the uncertainty in our knowledge of the bathymetry?
Oh, such a good question. I would say, but it's like we discover new things about the bathymetry around Antarctica on a regular basis. So we're going to use the product that we have available to us at this time and be aware that in the future this might change. In fact, just after publishing this paper, some scientists in Germany contacted Garrett and say, oh, we discovered that bathymetry is totally different in this part of Antarctica. How does that change the melt rates? And it does change it a lot. The second part of the theory, excuse me, I'll take a brief moment. Here, second part of the theory is an explicit prediction for how much warm water transport should reach the ice shelf base. And it's going to take account both of the far-field oceanic conditions and the influence of the ice shelf itself. So conceptually, we're considering the same structure. We're looking at a 2D slice, including the ice shelf and the seafloor again. And we're interested in predicting this exchange, essentially. How much warm water flows in, how much cold water flows out. And we are inspired by the observation in various previous idealized and regional modeling studies of Antarctic ice shelf cavities that inflows of warm water, as they flow south, are steered eastward toward the eastern side of the ice shelf cavity as they make their way south. The reason for that is exactly what was hinted at in the earlier question. That the ice shelf, because it essentially turns any water that's in contact with it into fresh meltwater, or mixes it with fresh meltwater very rapidly, creates a very large change in the depth of the picnic line, or thermocline, through the action of the melt. And so, by thermal wind, you create a flow westward in the surface freshwater layer and eastward, on average, in the subsurface warm water layer. The assertion of the theory is that that eastward geostrophic thermal wind transport is equal to the southward flow of warm water. That's actually not a novel idea. It's appeared in various places in the oceanographic literature before in the context of buoyancy-driven flows, particularly in the context of the North Atlantic overturning circulation. But this is the first time we've applied it to ice shelf cavities. Thermal wind yields this scaling. It relates the transport of that warm water into the cavity to the density gradient between the warm water and the cold water, Coriolis parameter, the slope of the ice, which dictates the slope of the picnic line, and the thickness of the circumpolar deep water layer, which we scale with its depth above that hub, the bathymetric obstacle to its inflow. The second relationship we need is we're going to assume that the inflow transport of heat is entirely balanced by the latent heat of melting. So all of the effective heat transport into the cavity is used for melt, which, I mean, frankly, that just is an assumption of equilibrium. If it's the only other place it could go would be to change the temperature of the cavity. So as long as you're integrating over a long enough time, this kind of holds us to be true. Now, an important facet of this whole concept here is we're not trying to actually explicitly predict the melt. We're predicting the net heat transport into the cavity. And so in that sense, it is a conceptually different formulation of an ice shelf melt parameterization from any of the ones I showed you before. Combining those two equations gives you an explicit prediction for the melt rate averaged over the ice shelf in terms of quantities that we know from the geometry of the ice shelf that we can observe, the hydrography, and the hydrography of the water in the far field, which we know, which we can take from climatologies around Antarctica. So we have predictions of melt rate purely from external parameters. To give this a preliminary assessment, we use a suspiciously familiar looking process-oriented model, which is probably don't need to introduce. It's actually even simpler There's no wind, there's no sea ice, just a prescribed temperature and salinity stratification that's representative of Antarctica, warm below, cold above, Celsius below, pressure above, and an ice shelf. And this is a temperature surface, the 0 degrees Celsius temperature surface, which is, as you can see, actually in contact with the ice here, almost in contact.
And you don't have a trough in this one?
No trough. But actually, this is a very smooth bathymetry. We also ran cases with random bathymetries of various kinds. And there's lots of experiments that I can detail if you like, with varying widths of the ice shelf, extents of the ice shelf, depths of the grounding line, and various different heights of the thermocline offshore to test the theory. Comparison between the predicted melt rate and the observed melt rate is not perfect, but really pretty good, explaining 91% of the variance. So that's encouraging, but to be fair, if there was any situation in which you would expect this theory to work, it's this one. It's sort of designed to be as favorable as possible. There's nothing that could interfere with the theories. Just warm water, buoyancy-driven flow. There's no forcing except for the melt. What else can happen? So if it ever was going to work, it would work here. A harder test would be to take that theory and apply it to actual observations of melt around Antarctica, from a recent paper by Oceanic et al., which actually I've shown you this map before. And then, from that, we have multi-annual average melt rates over each individual of those 70 or so ice shelves around Antarctica. We have bathymetry, which may change, from that map, which this is showing the hub. The red contour is the hub, the isobath that's the least obstructed, the warm water has to rise above to access the Amory ice shelf. And we have World Ocean Atlas hydrography, temperature and salinity, which we take at the 1500 meter isobath. So that's really very far from the ice shelf grounding line where we expect most of the melt. Right? This is like hundreds of kilometers away. So we're definitely not cooking it by taking the hydrography right next to the ice. This is an example. From that hydrography, we get the depth of the picnic line, and we get the temperature of that circumpolar deep water that can peak over the bathymetry. We put all these parameters into our theory and compare it with what we observed. The blue arrows show the blue bars show the uncertainty in the observed melt rates on the y-axis. These are the predictions on the x-axis. It's more scattered than in the model, but all things considered, really rather good. Something like 80% of the variance explained, even in the observations, even in this very wide diversity of ice shelf cavities, some of which the theory really just should not work on because they have deep convection occurring in front of the cavity faces, which is not accounted for at all in the theory. The caveat there, of course, is that the ice shelves where this works the least well tend to be the ones whose area average melt rates are the lowest, and so they stand out less on a scatter plot like this. All things considered, it actually really works, to us, surprisingly well. I mean, there's some that are foam, perhaps, the most egregious outlier. So, this particular down here, I won't talk about it today, but these blue dots here are ice shelves that you might classify as cold. The temperature of the waters in the cavity is close to freezing, whereas the red ice shelves are warm. The temperature of the waters in the cavity is a few degrees above freezing. So those red dots are the ones where we expect this to work best. That's what the theory is formulated for. The blue dots, some of them it should be expected to work, but for the ones that have deep convection in front of the ice shelves, it shouldn't. And actually, Garrett's ongoing work has been extending the theory to account for those cases where you have deep convection in front of the ice shelves. And actually, it turns out with a little bit more consideration of the salt budget, we think we can do much better. We can actually do very well also in the area integrated melt rates over all these ice shelves. But I'm not going to talk about that today. So the take-homes from this are that we've shown that the observed undercurrent pathway that we think is the key pathway for transport of warm water to our ice shelves is in fact driven by the ice shelf melt itself, which kind of breaks the causality that the community has been approaching for how far-field atmospheric or climate variability drives change in these ice shelf melt rates. Inspired by this, we have derived a new novel geostrophic constraint on warm water inflow. It's really quite simple, really, just based on geostrophic balance of the flow inside the cavity, assuming it's the horizontal buoyancy gradient is set by the melting of the ice. And it actually surprisingly accurately predicts both idealized model and observed melt rates around Antarctica. What we're working on right now is extending this theory, as I said, to cold ice shelves, and actually Garrett has a NASA finessed project, which he's being supported to develop this as a parameterization for the NASA GISS model. Very briefly, as I wrap up, I would just like to point out that this idea of melting, driving, vorticity forcing, and driving circulation also works in glacial fjords. It's a little bit more complicated because the ice is vertical and there's subglacial discharge and stuff, but it basically, the same ideas hold in glacial fjords. And if you're interested in that, check out Ken Zhao's work. He was also one of my graduate students, and I was at Scripps as a postdoc. We have various other ongoing projects looking at other ways in which melt forces aspects of near Antarctic ocean circulation. The one I particularly like to highlight is led by Madeline Youngs, who's a postdoc, and she's just starting as faculty at UMD in January. She has been using a regional model experiments that simulate the melt of all of Antarctic ice shelves, and she's been trying to dissect the relative influences of atmospheric forcing versus the influence of the melt on ocean circulation around Antarctica, trying to identify how important is external forcing or the forced response versus the melt feedback. And the short version, without getting into the nitty-gritty here, is that they are comparably important and frequently opposite in sign to one another. And so it's a further evidence in support of the importance of considering the impact of the melt itself in the future evolution of the ocean circulation around Antarctica and the Antarctic Ocean. And with that, I will conclude, and thank you very much for your attention.
Thank you, Andrew. And we have a good number of minutes for questions. As per usual, we'll go with any grad students first. Anyone have a question for Andrew? Hesitation. Yes, please.
Yeah, so with this paper that's in prep right now, did you say that's more focused on the ocean, or are there some atmospheric components added into that?
This is ocean sea ice model only.
Okay.
So we take the atmospheric state from and the far field ocean boundary conditions from CMIP6, CM4 specifically, SSP 585 simulation at different times. And so we say, like, you take a future atmosphere like a future like atmospheric state, force the ocean with it. How does that? What kind of change does that drive? And we do that also in experiments where we essentially hold fixed the cavities, so you can't have a melt feedback. And we look at the differences to help us understand, to tell the discern between what's forced directly by the atmosphere versus what's forced by the melt of the ice shelves.
Thank you.
Yes. Go.
Is there much of a seasonality to these circulations?
Yes, especially in places that have convection in front of the ice shelf. So you can classify ice shelves broadly into three categories. Some are what we call warm, these ones down here, they're flooded with warm water. Some that you might call fresh, they're basically flooded with freezing temperature water that's still quite fresh. And some that are dense, so they are flooded by water that's very dense, formed by a rejection of salt as sea ice is formed near the front of the ice shelves. And these cavities that are, particularly the ones that are dense, it's a very seasonal formation of dense water that seasonally dumps, especially in the winter, dumps a ton of dense water in, and then in the summer is much more, is not necessarily shut off, but much weaker. And so those cavities in particular do have strong seasonality. There's also strong seasonality in the insulation, obviously, at these latitudes. And so the upper waters of the ocean vary between what's called winter water, which is cold and a bit salty, and then summer water, which is much fresher and very warm. and those summer waters also intrude into the ice shelf cavities and cause melt in some places, but it's not much compared with the melt induced by deep warm water intrusions. So I would say usually the seasonal cycle in melt is quite low, except for some unusual cases where you've got particular where the melt happens to be dominated by inflow of warm summer waters. But in most cases, it's a relatively muted seasonal cycle. Thank you.
Rudra.
So great talk, Andrew. I have a quick question from the modeling side of the model. That do you think your results might be affected based on whether the model has isopical coordinates when you run the model, or isobats, or especially when it comes closer to the grounding line?
Well, I would say yes. So it depends what you're asking about. I think the ice sheet model under comparison project established pretty quickly that the coordinate system you use to represent ice shelf cavities makes a huge difference to the simulated melt and the boundary layer structure. And really, what matters is just how many grid points you have in that couple tens of meters close to the ice. So yes, I would generally expect changes based on the coordinate system. However, on the other hand, I would say this theory would say that basically any model should simulate a similar hydrographic structure in the cavity, unless it was wildly convecting for some reason in the cavity. And so our expectation is that the melt rate is relatively insensitive to the model representation, but maybe it is sensitive to the particular 3D geometry of the cavity or things like that. So, that might be, maybe I'm being over optimistic there. But the part of the appeal of this for us was that it's not dependent on the boundary layer processes. It's purely dictated by just the large-scale hydrographic structure of the cavity, which hopefully makes it insensitive to those details. Thanks.
For those of you who are taking 660 right now, I hope you pay close attention, because the nanodesica 99, I might just switch it out with phenocanic and Stewart 24 for the geostrophic transport.
Yes, indeed.
Anyway, sorry. Leo.
Really great talk. Really enjoyed that. How vital is the bathymetry and the connection of the ice shelf to the seafloor to this type of circulation? Could it also exist for free floating ice like in the Arctic, or is that pretty much exclusive to the Arctic?
So are you thinking about Arctic sea ice?
Yeah, just is there some kind of analog up there, or is it requiring that there has to be that ice cavity there?
Yeah, the closest analog is the Greenlandic fjords, where you do have similar concept applying. Some Greenlandic fjords also have ice shelves, so they actually have a shelf here, but only a few of them. Most of them just have a wall of ice, and then you see the geometry is slightly different, right? You do have rapid melt very close to the ice, and you do have this kind of boundary layer of activity over here, but to first approximation, the ice thickness in the fjord are flat instead of being strongly tilted down toward the grounding line like they were in that hypothesized ice shelf cavity. And so that geostrophic constraint that we use doesn't really apply anymore. And instead, the relevant considerations are, yes, the vorticity input, which comes from upwelling of waters by melt and discharge at the ice shelf base, the recirculation and the feedback of that recirculation on the melt. No, that's it, and how those two things interact with one another. So in terms of sea ice, I would say I don't see a parallel with sea ice. I would say that's a fundamentally different situation, because the ice shelf is, in part for various reasons, among them the ice shelf really entirely shields the ocean from the atmosphere. It's hundreds of meters of ice. The sea ice is dynamic, it moves, it exerts stresses on the ocean itself, as well as exchanging thermodynamic properties with the ocean. And so it's kind of qualitatively different dynamic between the ocean. And also the sea ice is driven by the ocean. There's yeah. So I would say I wouldn't aim to draw a parallel with the Arctic sea ice, but with the fjords, absolutely.
Okay, we had Hamish and Nicola, and maybe Colin.
So you convinced us that the causality doesn't come from the atmosphere, but does the atmosphere at least modulate this process? Like
Yes,
the magnitude
it
of the emergency load, does that impact?
Yes.
We don't
Yes.
care about the atmosphere at all here.
Yeah, so exactly. I actually think that this idea is not, the idea that this leads to this is not fundamentally wrong. But I think that I suspect, but don't have evidence for it at this time, so this is going to be pure speculation on my part, is that the Munson low fluctuating is indeed driving kind of large-scale oscillation or heaving of the temperature surfaces adjacent to this part of the continental shelf. It does produce large-scale changes in the temperature of the continental shelf that do lead to changes in melt. But that the specific formation, the formation of undercurrents specifically, is a symptom, not a cause of the melt. Yeah.
Yeah, I have two questions, but I can ask one. You mentioned it briefly at the end when you were comparing the results of your melting model with actual observation. You say that, for example, for the West ice shelf and the Rhone ice shelf, it should not work because it's large ice shelf with their own internal circulation. So two questions in one. Why do you think it worked almost okay, and how we can improve it? Do you have an idea how to improve your model by parameterization to take this big ice shelf case into it?
Well, that is an astute question because there's a significant detail here, right? Area average melt rates. In area average melt rates, the Ross and especially, but also the Waddell ice shelves are small numbers because they're just such large areas. But if you were to make this plot using total melt, then it would not look so good. And that's where you need to work on the accuracy of the theory. And that's what Garrett's done in the past months. I don't have the slides here. Is figure out how to adapt this theory to the case of when you have convection in front of the ice shelf. I think that's your question. Yeah.
Okay. It is past 4:30, so thank you again. Thank you everyone for